8, video 16. In this video we will talk about how to determine pH of weak acids. Now this is connected to the concept of equilibrium. We'll do weak acids and bases. Maybe we'll throw a base in there. We'll focus mostly on acids. And equilibrium, remember, is used to represent weak acids in solution. Really there's no other way of representing a weak acid properly unless you have the concept of equilibrium. An equilibrium system have what are called equilibrium constants. So here's a bunch of acids listed along with their equilibrium constants. So here, hydrochloric acid, which you'll recall is a strong acid, has a Ka that's so large that we essentially ignore it, and we don't call hydrochloric acid an equilibrium system. Same thing happens for these, sulfuric acid, nitric acid. These guys have really, really large equilibrium constants. Nitric acid is actually given right here, about 20, which is actually so large that you can call it large, and you can ignore nitric acid in terms of equilibrium. But beginning down here with the weak acids, and most of the acids in the world are weak acids, they actually have a constant, an equilibrium constant. So here is, we talked about carbonic acid. Carbonic acid's equilibrium constant is 4.3 times 10 to the negative 7. Not very strong. Down here is hydrogen cyanide, and its constant is really small, 10 to the negative 10th. And ammonium ion is even smaller. So this shows you the Ka. We're going to use these Kas to figure out how to get the pH of these weak acids. So chemists have obviously determined the way to get the pH of weak acids, not only of strong acids. Now, we can express the weakness by listing something called pKa. So just like we have pH, which is the power of hydrogen, pKa is the power of your Ka. So, and pKa is defined as a negative log of Ka. So we're taking these equilibrium constants and just negative logging them, and here's what we're getting. We're essentially pulling out, remember the negative log essentially pulls out the power. So the power here is about 3, and that's why the pKa is about 3. It's not exactly 3 because this is not exactly 1. So here, for a number of different acids, if you simply negative log their Ka, you get what's called a pKa. Now, the higher the pKa value is, notice they're just increasing here, the weaker the acid. And that's because what happens is the higher pKa means this is a smaller power, which means it's a smaller number, which means you have a weaker acid. And the way to remember this is kind of like pH. The higher the pH, the less acidic the solution is, the weaker the acid. So the higher the pKa, the weaker the acid. So think of these as we're slowly inching up toward a base. So high pKa's have weak acidity to them. And here are some strange acids. Now, hydrozoic acid is a strange name, but this is not NH3 but HN3. Interesting, hydrozoic acid. All right, now to get the pH of weak acids, well, first of all, to get the H plus before we get the pH is simply the negative log of H plus. But to get the H plus, we're simply going to give you an equation. Now, this equation comes from equilibrium, and there's a lot of concepts hidden in this. So we're simply going to give you an equation and simply use the equation on the test to solve for it. But what you do is you take the square root of the product of the Ka, the equilibrium constant, and the Ha, which is the acid concentration. Remember, the brackets actually represent molarity, moles per liter. So if you have the concentration of the acid, you have to know its Ka. You simply multiply those together, square root, and you get the H plus. Same thing with a weak base. If you have a base, to get the OH minus, you square root the Kb. This is the equilibrium constant for the base times its concentration. And you'll get the OH minus H plus. From there on, you can negative log it to get the pH or pOH. Let's do exactly that. So we want to find the pH of a 0.15 molar solution of acetic acid, the famous vinegar. This is good old vinegar. So the Ka of acetic acid is actually 1.8 times 10 to the negative 5th. So the equation that we showed you to get H plus, you simply take the square root of your Ka times your Ha concentration. Ha concentration is 1.15, Ka is 1.8, E negative 5. So really, this is a plug and chug type of business. So we got 1.8 E negative 5 times 0.15. Go ahead and plug this into your calculator and take the square root of it. So I got 0.8 E negative 5 times 0.15. Let's take the square root of that. get ourselves an answer that's 001643. Now this is actually molarity because what we're solving for is H+. If we want the pH, pH is the negative log of that. So we'll take the negative log of 0.001643. So go ahead and take the negative log of it, which should give us 2.78. We have two sig figs, so 2.8 for the pH. And that is the pH of the weak acid. Now, if this were a strong acid, what happened is you would simply negative log the 0.15. So if it were HCl, so say we got HCl here at 0.115, for HCl you simply negative log 0.115. That's because all of it dissociates. Here we couldn't negative log 0.15 because not all of it dissociated. How much of it dissociated? Only this much. So this equation actually solved for how much of the acid dissociated. It's nice and simple, pretty neat how simple it is, but only a small fraction of the 0.15 dissociated, actually about 1/100th of it. This is almost 0.0015, so about 100 times less dissociated. And if you were to negative log 0.115, you'd get a pH that's 0 point something, wouldn't you? It'd be exactly, if we negative log, you actually get 0.82 for the pH, quite a bit lower. Remember, the difference between here and here is not a little bit, it's 100 times bigger. 2.8 to 0.8 is about 100 times. And that's because their concentrations are about 100 times bigger. Well, between here and here, sorry. The concentrations of the hydrogen ion are about 100 times bigger. And that's how this works. So simply, just plug into the equation. But the concept here to understand is that weak acids do not dissociate completely. They dissociate partially. Equilibrium can tell you exactly how partially they dissociate. Alright, let's do the same thing. Let's do ammonia since we've talked a lot about ammonia. So we can now get the pH of a ammonia solution, 0.200 molar solution of ammonia. So in this case, we've got the Kb, and solving for it, the OH minus is simply the square root of Kb times your base concentration. So if we plug in Kb, 1.8, E negative 5, you actually notice that the number for ammonia is the same as the number for acetic acid. The Kb and Ka actually match, which is an interesting coincidence. 0.200. Right, if we do this, go ahead and plug this in your calculator. We got 1.8 times 0.2, and then we'll have to square root that. See what we get. So actually very similar to last time. 0.001897. This is the molarity of OH minus concentration. To get the pH, we have to first get the pOH. The pOH will be the negative log of that number, 0.001897. So go ahead and let's get the negative log of this. So here we get 2.72, and then to get the pH, we subtract 14. pH is 14 minus that, which gives us, for sig fig wise, 11.3. 11.3. So because we have three sig figs in this case, we actually 2 sig figs from here, but the 7.2. If we cut it off at 7.2, when we're subtracting, we got 1 decimal place because this is exactly 14.000. That doesn't limit us, so we get 11.3 for the pH, which is in keeping with a base, high pH, but not very high because we have a weak base. If we had 0.200 molar of a strong base, say sodium hydroxide, then that pH would be closer to 14. In fact, it'd be about 100 times stronger again, like we saw in the last time. So it'd be about 13.3. Alright, this wraps up the video for us and the chapter for the time being of equilibrium on acids and bases.